Let's start LAB2 question 2. Build project. Click the debug button and the step over button. Initially, we set watch 1 by adding the variable list in .data segment. You can see the variables such as alvar, svar, yvar, and zvar have already been declared and they will be used in system. Click the step over button. You can see the arrow point to the next execution to be executed, which is line 1. Click step over again to move the value of x bar, which is 26 in decimal, into register EAX. The EAX register is highlighted to red to indicate that its value has changed during execution. The value of EAX register same as the value of x bar, which is 26 in decimal, but the register stored in the hexadecimal, so the actual content is 1A. Click step over to negate the value of register EAX. 1A become FFFFFE6, which is negative 26. Click step over to move the value of y bar, which is 30 in decimal, into register EBX. The value of EBX registers same as the value of y bar. Click step over to subtract the value of z bar, which is 40 in decimal, from register EBX. The result of 30 minus 40 is negative 10, which is FFFFFF6 is stored in EBX. Click step over to add the value of register EBX to register EAX. The result of negative 26 plus negative 10 is negative 36, which is FFFFFFDC in hexadecimal is stored in the EAX register. Click step over to increment the value of register EAX by 1. In hexadecimal, C plus 1 is equal to D. The content of EAX become FFFFFFDD in hexadecimal. Click step over to run the last line, which is line 7, to move the value of EAX into alvar. The value of alvar is equal to the value of EAX, which is FFFFFFDD in hexadecimal. Let's start the LAB2 question 4. Build project. Click debug and step over button. Clear the previous variable list and add the new variable list for this question. Click step over to run line 1 to move the value of var1, which is 40 in decimal, into register AX. The value of AX same as the value of var1, which is 0028 in hexadecimal. Click step over to run line 2 to move the decimal value 5 into register BX. So the content of register BX is 0005 in hexadecimal. Click step over to run line 3 to multiply the value of register AX, which is 0028 in hexadecimal, by register BX, which is 0005 in hexadecimal. The result of multiply 40 by 5 is equal to 200 in decimal, and C8 in hexadecimal is stored in DXAX. The content of register AX is 00C8 in hexadecimal. Click step over to run line 4 to move the value of var2, which is 10 in decimal, into register BX. The value of register BX same as the value of var2, which is 0008 in hexadecimal. Click step over to run line 5 to subtract the decimal value 3 from register BX. The result of 10 minus 3 is equal to 7 in decimal and hexadecimal is stored in register BX. The content of register BX is 0007 in hexadecimal. Click step over to run line 6 to divide DXAX by register BX, which is 0007 in hexadecimal. The value of DX is 0000 in hexadecimal, and the value of AX is 00C8 in hexadecimal. The result of divide 200 by 7 is equals to 28 remainder 4. 20x is quotient, 4 is remainder. In 16-bit division, the quotient is stored in register AX, and the remainder is stored in register DX. So, the value of 28 in decimal and 1C in hexadecimal, which is quotient, is stored in register AX, and the value of 4, which in decimal and hexadecimal, which is remainder, is stored in register DX. Click step over to run line 7 to move the value of register AX, which is 001C in hexadecimal, into var4. The value of var4 same as the value of AX, which is 001C in hexadecimal. Let's start to complete a full program to execute the code snippet 2. Include IRBINE32.inc. Data segment.data. Since there is no data definition statement, so data segment is not required. Code segment.code. Main PROC to define the beginning of a procedure. Name main. Call down regs to display the content of all register. Exit. This is a macro that end program execution. Main ENDP to define the ending of main procedure. And main. The program is completed. Let's start to run our code. Build project. Start without debugging. You can see the content of all register. EAX is 001A03X0, so AX is 03X0. AX register consists of AH and AL register. In the 8-bit division, AH is used to store the remainder, which is 03 in hexadecimal, also 3 in decimals. The AL is used to store the quotient, which is X0 in hexadecimal, 128 in decimal. So we know that the result of divide X02 in hexadecimal by 10 in hexadecimal is X0 remainder 3. Besides that, we also know the comment provided is wrong. Actually, quotient stored in AL register and remainder stored in AH register.